In this video, I'm going to talk about the exchange forces, and this exchange forces I'm going to break it into two parts because the math when you expand it, it's a little bit long, so I'm going to break this into two parts. But let us begin. So if two particles are distinguishable, and one is in psi A, the other one's in psi B, remember the combined wave function is then psi x1, x2 is equal to psi A, x1, psi B, x2. I already talked about this formula in my previous video. If you don't know this, I recommend you guys to check this out. But what this is saying that when you have two distinguishable particles, the combined wave function of these two can be written as the product of their own individual psi A and psi B, x1, x2. Right, so what this means is that we can break down the combined wave function already into two individual one particle wave function. And x1, x2 here are the spatial coordinates. Sometimes the textbook uses r1, r2, but they're interchangeable. So x1, x2, r1, r2, whatever one that you want to use, they should be the same. And if you remember, for identical bosons, so for bosons, psi plus x1, x2, this is the formula for identical bosons. x1 psi b x2 plus psi b x1 psi a x2. And remember, this is the formula for identical bosons, and you have the plus here, whereas for fermions, it's going to be psi minus, right? And if you remember in my video, I also talked about how for bosons we need to ensure they're symmetrical, and for fermion we need to ensure that they're anti-symmetrical. So just a quick reminder, that is what the negative sign here do, right? The negative sign here ensures that our fermion, so this is identical fermion, ensure our fermion is anti-symmetrical. And our positive sign here for boson ensures that it is symmetrical on their exchange. But that is not really related to the topics which we're going to talk about today. So the next part would be we want to calculate the excitation value of the square of the separation distance between two particles. So we have particle x1 and x2, so their separation between them is going to be x1 minus x2. So we want to calculate the square of that, and then the excitation value of that. So the excitation value of the square of the separation distance between these two. And if you have x1 minus x2 inside, you can square inside, you could expand this into x1 minus x2 times x1 minus x2. And if you've done high school algebra, you know that this is equal to x1 squared minus x1 x2 minus x2 x1 plus x2 squared, right? So this is going to be x1 squared minus 2 x1 x2 plus x2 squared. And if we want to find the excitation value of this, then this is just going to be about finding the excitation value of each individual terms, right? So this is going to be excitation value of x1 squared plus excitation value of x2 squared minus 2 times excitation value of x1 x2, because 2 here is the constant, right? So this is the expression we have here. And for our case 1, where it is distinguishable particles, so distinguishable particle, right? Okay, let's first look at this first term. So for our distinguishable particles, this first term, so we want to find the excitation value of x1 squared. And I'm not sure if you guys remember the definition of excitation value, right? If we have some observable quantity O, then the excitation value of O by definition is going to be the integral of psi complex conjugate times O times psi, and then dx, let's say here for the variable, and right. So this is the so-called definition of an excitation value for an observable O. So the case for our x1 square here is that our case of observable here is x1 square. So our operator O in this case is just going to be x1 square, right? So if we follow the same formula, x1 square, this is going to be, in fact, one of the key differences here between x1 square and O is that x1 square actually relies on both x1 and x2, right? Because the system that we're considering is a two-particle system, like the total wave function should be both a factor of x1 and x2, right? So in this case, we're gonna have double integral psi complex conjugate x1, x2, and then our x1 square between them, same as how our O is between these two, and then psi x1, x2, dx1, dx2. So this gives us the excitation value of x1 squared, right? Because remember, the key differences that we have from this one and the O is that our x12 actually is a part of a wave function that consists of two variables instead of one, which is what we have for O. And this is the conjugate part, which stands for this part, right? And our O, which is our x1 squared, is this part. And our psi x1, x2 is this part, right? So basically it's the same expression, but what we have down here is that the wave function consists of two variables instead of one. And we have dx1, dx2 because we have two variables in our case. We have x1 and x2. So therefore we should have the corresponding dx1 and dx2, right? And then we have the double integral for the same reason. And now, if you look above, the initial expression that we have, so let's copy this and bring it down. This gives us the expression for psi x1, x2, which is what we have here, psi x1, x2. So we can replace our psi x1, x2 and our conjugate psi x1, x2 with this expression right here. So this is going to become double integral psi conjugate a x1 psi conjugate b x2. And then we have our x1 squared squeezed between these two, and then psi a x1 psi b x2. So basically dx1 dx2. So basically what we have done is that we have substituted this expression into our function here, right? So that's what we have done. We have substituted the expression that we have initially into this. So these two are the same. It's just that we express them differently. So if we keep breaking this down, if you want to group the like terms, because remember, psi x squared is equal to psi x conjugate times psi x, right? So in this case, we can group the like terms. So we have psi a conjugate x1, we have psi a x1, and we have psi b conjugate x2, and we have psi b x2, right? So if we group, let's use a different pen here, color. So if we group this and this, and we group this and this, we obtain the following, which is psi a x1 square psi bx. Oh, I forgot to have the x1 in between, x1 square in between, right? With psi bx2 square dx1 dx2. Right, because basically what we have done is we have grouped these lie terms with psi a conjugate x1 psi a x1, right? And these two, if you group them together and make them multiply each other, you get this term. And then the same goes for psi b x2. And one very important thing to notice here is that we can actually use a separation of variable here, because psi a x1 depends only on x1, and psi bx2 depends only on x2. So we can group the lie term again and break this down to the following. So we have psi a x1 square x1 square dx1, and psi b x2 square and dx2, right? We have grouped the lie term again. We can break this down because remember, our this term here does not rely on x2, and our this term does not rely on x1. So we can really separate these two integral into this following formula. They represent the same thing, but I have basically isolated variables, so x1 to x1, x2 to x2, and they don't depend on each other. And what we have here is that this is actually going to equal to 1. So the second term over here is going to equal to 1. Because this is, if you recall in chapter 1, this is just going to be the normalization, right? So we have, when we have integral of psi conjugate x times psi x dx, this is just going to be equal to 1, right? This is the formula for normalization, and the same goes here, right? If you expand this, you get a similar formula as this. So the second term here is just going to be equal to 1. So what we really have for the expectation value, x1 square, is integral. So is this the first term right here? Integral of psi a x1 square x1 square dx1. So this is really what we have. And if you recall that for a single particles, if you want to find the excitation value of that particle's x squared, so its position squared, this is going to be integral of psi conjugate x times x squared times psi x dx, right? And if you compare this formula, this is if you further break this down, this is going to be psi x and then x squared, right? dx, right? And if you compare this formula with what we have here, you realize that they're exactly the same formula, but you're missing a right here for the psi a. So in this case, these two, we can write them as equal to each other. So psi 1 squared is actually just going to be equal to x squared a here. And if you're wondering where did the 1 go, well, in this case, since we're only considering a single particle, so x1 squared, right, it is really the same formula as a single particle square, right? The case we're looking at here for x1, which is the particle 1, and x squared, which is one particle, they're exactly the same thing. So having one or not having it doesn't really make a difference here. So therefore, the one here I didn't write, the textbook didn't write this too. But what matters here is that you have this a that represents the state. So if you follow the same logic of what I have done above, you will know that for x2 squared, this is going to be x squared b. Following the exact same process that I have done here, but for x2 squared. So if we bring this formula down, copy this and paste this. You'll realize that, well, we have x1 squared, we have x2 squared, but we're missing x1, x2. So let's find the excitation value for x1, x2. So for x1, x2, we have, so excitation value for x1, x2, this is going to be, well, it's going to be double integral. And psi conjugate A x1 psi B conjugate x2, and then you have x1, x2 squeezed between them, and then psi A x1 psi B x2 dx1 dx2. And if you do the separation thingy again for this integral and group the like terms again, like what we did for the excitation value of x1, you're gonna get a formula integral of psi A x1 x1 psi A x1 dx1 times the second part, which is integral of psi conjugate B x1 x2 no x2 here, and psi A conjugate no sorry, it's my bad. It's like sometimes when you write this, you get too deep into thinking it that you forget what we really have here is psi conjugate A x2 psi conjugate B, no conjugate for this. Now we're grouping the term of A and B. So I am wrong again. This should be psi B x2 psi B x2 and dx2. I just had to check again. No, I'm also missing x2 here, right? Because the x1 goes here, the x2 goes here. So what you get is x1 times dx1, don't forget that, times psi psi bx2 square x2 dx2. And if you simplify this is going to be, well, the first part is just going to be x A, the second part is going to be x B. For the similar logic that I follow above for this, right? But you just had to check the excitation value of x yourself to know that this is going to be excitation value of x A and this is going to be excitation value of x B. So therefore, for our distinguishable particle, the excitation value of the square of the separation distance between them is going to be simply x squared A plus x squared B minus 2 times x A x B. So this is what we have here for our distinguishable particle. And in my next video, I'm going to talk about the next case and how all of this sum up and what the exchangeable force is, right? In this case, we talk about the distinguishable particles, but we need to talk about case 2 where there's identical particles, which I'm going to do in my next video. And I'll see you guys in the next video.